The question we are solving now belongs to test series 5. It is of network theory subject. In specific, it belongs to transient response analysis of RLC circuits. As per the question, there is a circuit given as shown in the figure. The circuit contains a 1 volt voltage source and a switch S which is closed at t equal to 0. The voltage source is connected to the network shown through the switch. The network contains a 1 ohm resistor which is in turn in parallel with a series combination of 1 ohm resistor and 1 farad capacitor. The current through the capacitor is given as IC of t. It is given that the circuit is initially relaxed. We need to find IC of t for every t. So from the given circuit, we see that for t less than or equal to 0, IC of t is equal to 0 ampere because the circuit is initially relaxed. Now let us analyze the circuit, and also during this time period Vc of 0 minus is equal to 0 volts, where Vc of t is the voltage drop across the voltage across the capacitor terminals. Now let us analyze the circuit for t greater than or equal to 0. So for t greater than or equal to 0, we need to find IC of t, which can be expressed as C into dVc by dt. So first let us find Vc of t. So for finding Vc of t, we need the initial value of the voltage across the capacitor, which is given as Vi is equal to Vc of 0 plus is equal to Vc of 0 minus is equal to 0 volts. And the final value of the voltage across the capacitor is equal to Vf is equal to Vc of infinity, which can be expressed as 1 volt, because at steady state capacitor acts as open, and during this time period the equivalent circuit can be drawn as shown. As the capacitor acts as open, the complete 1 volts appears across the capacitor terminals, because of which Vf is equal to Vc of infinity is equal to 1 volt. So, and also we require the time constant tau, which can be expressed as R equivalent multiplied by C, where R equivalent is a resistance seen from capacitor terminals, which is 1 multiplied by the capacitance, which is 1 farad. So tau is equal to 1 second. So from this data, we can write Vc of t as Vf plus Vi minus Vf multiplied by e power t minus tau. So upon substituting the values we have got already in the expression for Vc of t, we see that Vc of t can be written as 1 minus e power minus t u of t. But this is the voltage across the capacitor terminals for t greater than or equal to 0. From this, IC of t can be written as C into dVc by dt, which upon simplification becomes e power minus t u of t ampere. For t less than or equal to 0, IC of t is 0 ampere, and for t greater than or equal to 0, IC of t is e power minus t u of t ampere. So for every t, IC of t can be expressed as e power minus t into u of t ampere. So from this, we see that the correct option representing the current through the capacitor can be written as B.